Hello and welcome to our first video in the discussion of partial differential equations. And in this video, we are going to take a look at the heat equation. Before we begin, let's briefly outline what are partial differential equations about. In previous classes, you've seen ordinary differential equations, which describe a process in time. And in those differential equations, the unknown was a function in one variable, the time variable. Partial differential equations can be thought of as the more complicated version of ordinary differential equations. Again, you've got an unknown function, but this time the unknown function does not only depend on one single variable, such as time, but it depends on many variables. For example, on time and space. And in this partial differential equation, you've got derivatives in different variables, different partial derivatives. That's why it is called a partial differential equation. Many important partial differential equations describe physical phenomena that take place both in space and time. There are plenty of examples for partial differential equations, and the most basic one, which we are going to have a look at here, is the heat equation. The heat equation is a prototypical partial differential equation that describes the diffusion process. As the name already suggests, the main application is the description of heat diffusion. For example, you put in a hot piece of iron into a large bowl of water, and then you would like to describe how does the heat diffuse from the hot iron into the larger bowl of water. That is a physical process that takes place both in space and time. The heat equation obviously gets its name from heat diffusion, but it also has many other applications. For example, it describes the diffusion of solvent within a solute, such as, say, salt and water. If you cough, then you distribute various particles in the air, and their distribution in space and time can be described also by a diffusion process, akin to the heat equation. There are plenty of other examples for heat equation type processes outside of physics and biology. For example, in finance, we've got the so-called Black-Scholes equation, and in quantum physics, we got the Schrödinger equation, and the heat equation also is important in describing processes in probability theory and information theory. So there's an abundance of application for that. In all those cases, we think of a diffusion process that takes place in space and time. You've got a spatial environment where we've got a distribution, and we want to describe how this distribution evolves over time. In order to get some intuition for that, let us derive the heat equation in three-dimensional space, and then we specialize that to the one-dimensional case. Now, doing the description in three-dimensional space is helpful because then it's easier to visualize the principal ideas, the underlying ideas of how to derive the heat equation. But later on, mathematically, we focus only on the one-dimensional case. We focus only on the case in one dimension. So let us suppose that u is a function depending on the spatial position x and the time variable t that describes the density of heat in space and time. The heat equation will be derived by two constitutive equations. The first one is known as Fick's law, and the other one is known as continuity equation. Let's have a look at the two. The first one is known as Fick's law, and it states that heat flows in the opposite direction of the gradient of the heat distribution. We put this into a formula as follows. Let's suppose that P, a vector field, describes the flow of heat in space and time. So Pxt tells us what is the direction of the heat flow at position x at time t. Now that flow, according to Fick's law, equals negative kappa times the gradient of the heat distribution u at xt. In that context, kappa is just some parameter which describes material properties. Generally speaking, kappa can be thought of as heat conductivity. So Fick's law tells us that the flow of heat is in the opposite direction of the gradient, proportional to some material parameter, which we denote by kappa. Now, second, we've got the so-called continuity equation. And here it is actually helpful to have a look at a three-dimensional setting just for the sake of visualization. Let us suppose that we've got some volume denoted by V, and we're interested in the amount of heat contained within that volume. The amount of heat contained within the volume V is just the integral of the heat distribution U over the volume V. Now, how does the amount of heat change in time? If we want to describe how the amount of heat contained in the volume V changes in time, we can express this in terms of the time derivative d over dt of the integral over V of uxt dx. That's the left-hand side of the second equation. And generally speaking, there are two influences here at play. On the one hand, over the volume V, we have got a source or a sink term, denoted here by F. Fxt tells us whether heat is produced or consumed at any point, at any position x and any time t. For example, whenever F is positive, it means that heat is produced, maybe there's a fire, or a chemical reaction that produces heat. Whenever F, however, is negative, it typically denotes that heat is consumed. For example, there might be a chemical reaction that consumes heat. The presence of a source or a sink term is just one way how the amount of heat in the volume V may change over time. The other influence is because of the heat flow, even if there's no other source term. Generally speaking, the amount of heat flowing in or out of the volume V can be described as the surface integral over the surface of V of the vector field pxt, the heat flow, multiplied with the normal direction n, multiplied with the outer unit normal n of the surface. That is the second term on the right-hand side of the second equation. If P is in the direction of the outer unit normal, then heat is flowing out of the volume, which is why we got the minus sign in front of it. Generally speaking, that type of argument is something you've probably seen already previously in Analysis 3 in your class on vector calculus. That being said, it's a good opportunity to visualize the continuity equation. Suppose that I've got some generic domain within three-dimensional space. It may be a ball, it may be a square, or something else. Now, generically, we can draw the outer unit normal along the surface of the domain. Let us indicate this here on this drawing. These are vectors at every point of the surface that are perpendicular to the surface and point outwards. And of course, which have a unit length. So that's a geometric setup. Now let's suppose we've got a flow of heat within this three-dimensional setting. Let's say all the heat is flowing to the right. So the heat, as it flows, might at some points enter the domain, and at other points, heat might be flowing out. So how is this related to the surface integral that we've seen before? In order to recap that, let's first take a look what happens when at any point of the boundary, the direction of the heat flow is also in the direction of the surface normal. For example, that is the case on the right. There, the heat is flowing in the direction of the surface normal, which indicates that it is leaving the domain. What happens if the flow is in the opposite direction of the unit normal? That is the case on the left. That indicates that heat is entering the domain. Finally, what happens if the flow is perpendicular to the outer unit normal? That is the case, for example, here at the top. Well, in that case, nothing enters. So to speak, the flow just scratches the surface of the domain without contributing anything to the amount of heat contained therein. Now, these three special cases all correspond to the inner product of the flow direction and the outer unit normal. Wherever heat is leaving, the product of the heat flow times the outer unit normal is positive. Wherever heat is entering, the product of the heat flow and the outer unit normal is negative, because these two arrows are in the opposite direction. And in between, whenever the product between the heat flow and the outer unit normal is 0, just means that those two vectors are perpendicular. In that case, nothing happens. No heat is entering or leaving. Based on that geometric intuition, it makes sense to describe the amount of heat leaving using a surface integral. So how do we get from this continuity equation and Fick's law to the heat equation eventually? Let us start with that surface integral. And for that purpose, we recall Gauss' law. Take a look again at the surface integral of the heat flow P times the outer unit normal. According to Gauss' law, also known as the divergence theorem, that equals the integral over the volume itself of the divergence of the heat flow. So we transform this surface integral into a volume integral again. We have the volume integral of nabla times the vector field P xt dx. Again, it's just an application of the theorem that you've already seen previously in your classes on vector calculus. And next, we can apply Fick's law eventually. We know that the heat flow is a negative gradient of the heat distribution U times this material parameter kappa. And for that reason, we see that the integral equals negative the integral over the volume V of the divergence times kappa times the gradient of U xt dx. So we've transformed the surface integral into a volume integral that we can express in terms of the heat distribution U. And now we can plug this into the continuity equation. That is the second line of equations. For each volume V, we get that the time derivative of the integral over the volume of uxt dx equals the volume integral of fxt dx plus kappa times the volume integral of the divergence of the gradient of uxt dx. Now that is true for every volume, and heuristically we can now take infinitesimally small volumes. We just shrink the volume until we eventually get to point evaluations. And that leads us to the third line on the slide. Taking infinitesimal volumes, we finally derive the heat equation. And the heat equation tells us that the time derivative of uxt equals fxt plus kappa times the divergence times the gradient of uxt. Now there are different ways to write down the heat equation, and in the last line you see one popular way of writing down the heat equation, where we have got all instances of the unknown function u on the left hand side and all the data, the source term f that is, on the right hand side. D over dt, the time derivative of uxt, minus kappa times the divergence times the gradient of uxt equals fxt for all positions x and all times t. As already mentioned earlier, we have derived the heat equation in 3 dimensions because there it is easier to visualize. But for our discussion, we will focus only on the one-dimensional case, where the heat equation can be derived quite similarly. And in my personal opinion, Having seen the three-dimensional case actually makes it much easier to understand the one-dimensional case. So let's specialize to the 1D setting. And at this point, it's also a good opportunity to introduce boundary conditions and initial values in order to get a more complete mathematical picture of what partial differential equation we actually want to solve. In order to have some physical intuition, let us suppose that we have got a one-dimensional metal bar parameterized in space as the interval from 0 to L. That is our spatial domain. And let's suppose we start the clock and want to see how does heat evolve in that one-dimensional domain. In order for that setting to make physical sense, first we need some initial heat distribution to start with. And that is a so-called initial heat distribution, the initial condition. At time t equals 0, we have got an initial heat distribution which we denote by U0 x. Now furthermore, at the endpoints a equals 0 and b equal L, we assume that we have got a fixed temperature each, which may however depend on time, and we denote these by G index A of t and G index B of t, with any positive time t. So perhaps we have got some heat evolution going on within this one-dimensional domain, say this one-dimensional metal bar, but with some physical mechanism we keep the temperature on the sides under control. For our example, we have a cooling device or a heating device which keeps the temperature constant, and in fact in many situations, in many mathematical discussions that is, we will only consider the case where GA and GB are just constant 0. That is, so to speak, a simplified setting where we can discuss the most basic properties of the heat equation. Now, speaking of the heat equation, let's again simplify everything for the one-dimensional case. And again, this will be accompanied by a blackboard demonstration. So again, we've got Fick's law, and this time the gradient in the one-dimensional setting is just the spatial derivative, the derivative in x. So Fick's law tells us that the flow of heat Pxt equals negative kappa times the spatial derivative of u xt. X is again the spatial position taken from the interval between 0 and L, and t is any positive time. Kappa, just as before, is some positive material parameter. This material parameter will not be that important in the discussion. But it is important to keep in mind, however, that different materials will have different heat conductivity parameters. Kappa might be very, very small, in which case heat is diffusing only very slowly, and if kappa is very large, the material will be very heat conductive. Heat will diffuse out very fast. Similar to before, we've got the continuity equation. This time we not talk about volumes, but we talk about subintervals within this interval from 0 to L. So let us suppose that we have got a subinterval from x1 to x2, where x1 and x2 are two spatial positions contained within the interval from 0 to L. That is, x1 is greater than 0, less than x2, which is less than L. Let's take a look, how does the heat distribution evolve over this interval from x1 to x2? Well, certainly the amount of heat contained within this interval from x1 to x2, contained within that subinterval, is just the integral from x1 to x2 of u xt dx at time t. And if we want to know what is the change of the amount of heat contained in this interval over time, it makes sense to take a look at the time derivative of that integral. That's why we start with d over dt, integral from x1 to x2, u xt dx. Again, the change of the amount of heat in the subinterval, very similar to the three-dimensional case, is the sum of two influences. On the one hand, we have a source term or a sink term, fxt, which tells us whether at any position x and any time t, heat is produced or consumed by an external influence. That is the integral from x1 to x2, fxt dx. And then we've got the amount of heat leaving or entering the subinterval. That second influence on the right hand side is described by pxt evaluated at x equal x2 minus the value of the heat flow at x equal x1. Again, it makes sense to visualize that. In order to better understand the boundary term, let's have a look at the following. So we got the term pxt evaluated at x equal 1 and x equal 2, which is a notation that we know from the fundamental theorem of calculus. Explicitly, of course, that is px2t minus px1t. This value describes the amount of heat leaving the interval. In order to better appreciate that fact, let's recall that P denotes the flow of heat. A positive value of P at any position x at any time t indicates that there heat is flowing to the right, and a negative value indicates that heat is flowing to the left. Within an interval, the heat flow might be positive or negative. Inside the interval, that is, heat may be flowing to the right or to the left at certain points. But what matters in order to calculate the amount of heat entering or leaving the interval is only the values of P at the endpoints, no matter how heat is shifted around inside the interval. For example, in the graph shown here, at x1, P is positive, which means at x1 heat is flowing to the right, into the interval, entering the interval, and it's also positive at x2, which means that at x2 heat is leaving the interval. So at the right endpoint x2, a positive value of P indicates that heat is leaving, and conversely, a negative value at the right endpoint x2 would indicate that heat is entering, flowing to the left. By contrast, at the left endpoint, a positive value of P indicates that heat is flowing to the right, entering the interval, and a negative value indicates that P is flowing to the left, leaving the interval. Keeping that in mind, it is now obvious that the difference px2t minus px1t tells you how much heat is leaving the interval at the two boundary points. This value will be positive if in total more heat is leaving than entering. It will be negative if more heat is entering than leaving, and sometimes it may also be 0, which indicates that as much heat is entering as it is leaving. Now, with that observation out of the way, we can finally derive the heat equation in the one-dimensional setting. Again, we substitute. We take a look at the time derivative of the integral from x1 to x2 of uxt dx. And okay, we already know that equals, on the one hand, the integral from x1 to x2 of fxt dx. And now, with that substitution, we also see that additionally we got the term plus integral from x1 to x2 of kappa, the second x derivative of u, xt dx. Again, we can take what happens if we let x1 and x2 get very close. What happens if we take infinitesimally small intervals? And at that point, we then conclude that pointwise, the time derivative of u at xt equals fxt plus kappa, the second derivative of u in x, xt. And that is true for all points x within the interval from 0 to L and all positive times t. Now, as already mentioned before, we need to adorn this partial differential equation with initial and with boundary conditions. We have got the initial heat distribution, and that translates into the initial condition that ux0 equals u0 x for all x between 0 and L. That is, for all x within the interval. And in addition to that, for all positive times t, we have that u0t equals g0t, and that is the temperature at the left endpoint of the interval. And then on the other hand, ult equals glt. That is the temperature at the right endpoint of the interval. That's been plenty of theoretical discussion. So now let's have a look at a few visualizations, a few examples. How does the heat equation actually look like? And that can be described by taking a look at the heat distribution uxt as we plot it in space and then let it evolve in time. To begin with, we take a look at a very simple example, namely the heat equation over the interval from 0 to 1. And let's say we have got no source or sink term, that one is equal 0. We got Dirichlet boundary conditions, but we start with some non-zero heat distribution at the very beginning at t equals 0. The initial heat distribution, in fact, is very simple. Initially, everything is at temperature 0 except between 1/4 and 3/4, where we got a starting temperature of 1. That is what you are seeing here at the very beginning. You see the graph of the heat distribution at time t equals 0. And now let's start the heat evolution. As we expect, as time progresses, the heat diffuses out over the entire interval. The initial heat distribution was a piecewise continuous function with 2 jumps, where it changes from 0 to 1 and from 1 to 0 again. But as time progresses, this immediately smooths out. In the long run, the heat distribution is gonna converge to 0. That's because eventually all the heat gets eaten up, so to speak, by the boundary conditions. At the boundary points, the heat is fixed at temperature 0 in this model here. And so in the long run, everything gets cooled down to temperature 0. There are various other physical interpretations to this. So, for example, instead of thinking about heat diffusion, we could also think about diffusion of, let's say, salt and water. Maybe we start with some high concentration of salt, uniform high concentration of salt in the middle of the interval, and then we release it and watch how it diffuses. The second example again takes place over the interval from 0 to 1, and this time we start with a piecewise linear initial heat distribution. It starts with 0, then rises up to 1 in the middle of the interval, and then it goes down again. It rises up linearly towards the middle of the interval, and then it decreases linearly to 0 again. And as we let the heat evolve again over time. What this example demonstrates is that changes do not take place where the second derivative equals 0. So maybe there are jumps, maybe there are kinks in the solution, or maybe the second derivative is not 0. But for example, towards the outer slopes, what you see is that, well, since there it looks linearly, since there the heat distribution looks like a linear function, initially at least we don't have any change happening there, at least nothing visible. Most of the change takes place in the middle of the interval, where the second derivative is non-zero. Along the slopes, however, the second derivative just equals 0, as you can almost tell, as you can tell from the picture. And so it takes some time until those regions starts moving too. Another feature of the heat equation that is demonstrated in that example here is that kinks are smoothed out over time. So we've seen previously that jumps are smoothed out, but also kinks in the graph are smoothed out over time immediately. The solution gets smoother and smoother. And of course, as time goes to infinity, the heat distribution will asymptotically go to 0. Finally, let's take a look at an example where the initial heat distribution is 0, the boundary values are fixed to 0, but we've got a non-zero source term. Let's say the source term is non-zero in the middle of the interval from 0.4 to 0.6. Again, it's a piecewise constant function. 0 everywhere except within this interval from 0.4 to 0.6, where it equals 1. And then we let the heat evolve over time. Of course, the heat now increases in the middle of the interval, and at the same time, it diffuses out. That's why we also get heat outside of the middle interval. More and more heat is produced in the middle of the interval. More and more heat diffuses out throughout the interval. Now what happens if we let this run for some time? Will the amount of heat inside the interval go to 0? No, actually not. That is because we still have got fixed temperature 0 at the endpoints of the interval. What will happen actually is that we produce more and more heat, but then the second derivative towards the endpoints gets larger and larger, and so the heat will flow out faster and faster out of the interval. In the long run, as t goes to infinity, what we actually get is a steady state heat distribution. Eventually we get some equilibrium between heat production and the fixed temperatures at the boundary points of the interval. In the long run then, you get an asymptotically constant steady state solution. So at this point, we can make a few general observations on the fundamental qualitative properties of the heat equation. First, the diffusion process approaches a steady state solution if the data are constant. Second, information from the initial heat distribution at the very beginning is gradually lost over time. We see that everything smooths out over time, everything gets wishy-washy, and at the end, if you don't have any heat source or heat sink, you're gonna have just a zero heat distribution in the very end. Asymptotically, that is. And last but not least, related to that, kinks are smoothed out over time. Everything diffuses. That's why it's called a diffusion process. So even if your initial heat distribution has got sharp kinks or jumps, those kinks and jumps are immediately smoothed out and you get a nice smooth heat distribution just immediately. And the heat distribution gets smoother and smoother over time. At this point, we have derived the heat equation. We have had some physical intuition for the heat equation and its fundamental properties. And next, we will approach the solution of the heat equation. In fact, solving the heat equation mathematically already involves a few tools that might be known from numerical analysis, of partial differential equations. Our focus is going to be the approximation of the heat equation via Fourier series, and that will be done in the next lecture.